Here are two balls. Both are a similar size and mass, but one type will do this, and the other type will do this.
One night of magic rush, the start a simple touch. One night to push and scream, and then ring. 10 days of perfect tears, the colors red and blue. We had a promise ring, we were in love. Took off our hats out of love to lean on. Would it be good enough? To call our heads up, to lean on. Would it be good enough?
Why does this happen? Let's do it in a more scientific way. Oops, sorry, did you miss that? Look, they both drop from the same height. They both hit the ground at the same time, but one bounces to 37% of its original height, the other bounces to 93%. Look at this. The orange inelastic ball takes a measly 2 seconds to stop bouncing, but the green bouncy ball keeps going, and 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 going for 13 seconds. The secret to the ball's ability to bounce lies in its molecular structure. Let's take a closer look inside. Can we have some light, please? The main material inside bouncy balls is polybutadiene. Did you know that in 1999 the world used nearly 2 million tons of this synthetic rubber? Polybutadiene, as those of you doing chemistry will have guessed, is made up of lots of butadiene monomers. Each monomer contains 6 hydrogen atoms and 4 carbon atoms. These monomers link together in chains like this. As a monomer, butadiene has 2 double bonds between the first and second, and then the third and fourth carbon atoms. But as a polymer, there is only 1 double bond between the second and third carbon atoms, so this spare double bond is sometimes used to make crosslinks between the chains. When a non-elastic ball is dropped and makes contact with the ground, the kinetic energy from the fall is transferred into the ground. But when an elastic ball is dropped, the molecular bonds are twisted, causing the whole structure to compress. The kinetic energy is stored in these bonds electrostatically and thermally. That's why when you stretch a rubber band, it heats up. When no more energy is being put into the bonds, the energy stored in the bonds is converted back to kinetic energy, causing the entire structure to untwist and return to its original shape. The kinetic energy returned to the molecular bonds is sufficient to send the ball back in the direction that it came from. But what happens when we try to put loads of energy into these bonds? Surely there must be some point at which they can't take any more energy. If kinetic energy is equal to half the mass times the velocity squared, then increasing the velocity would increase the kinetic energy so much that the balls might not bounce, but break. This should do nicely to test that. 25 meters high means the ball will be travelling at about 22 meters per second and will have 24,500 joules of kinetic energy at the bottom. Is that enough energy to break the ball? There it goes. And it's bounced. Even 24 kilojoules of energy isn't enough to break the molecular bonds inside. But it will break, because with enough force anything will break. Let's see if this will do the trick. The ball starts at 40 millimeters in diameter. Let's see what happens when it gets squashed. And amazingly, it returns to its original shape and size. That's nearly half its original diameter. Let's try and break it now. There it goes. Let's see that in slow motion. See how the cracks propagate through the entire structure. Another amazing property of polybutadiene is its resistance to cold. All materials have a Tm, or melting temperature, but in addition to this, glasses and polymers have a Tg, or glass transition temperature. Above this temperature, materials are stretchy and rubbery, but below it they're brittle and glassy. Drop the temperature enough, and something soft and squishy like blue tack will go as hard as nails. Polybutadiene has a relatively low glass transition temperature of minus 90 degrees centigrade, so even in the harshest natural conditions on Earth, it will still be soft and springy. I wonder if you can guess what else polybutadiene is used for. It's resistant to cold, it takes a lot of force to break it, and it's very springy. Have you guessed it now? That's right, it's used for off-the-road, cold-weather tyres. Because they need to be tough, absorbent to small bumps in terrain, but very resistant to cold. So for those of you holding a bouncy ball in your hand right now, remember, it's not a toy, it's a scientific marvel.